So we've covered a wide array of techniques to test for the convergence of a given series. Okay, and this calls for a summary and to be thinking broadly about the strategies that we should employ when we want to test a given series. And now, just like with integration, when we first approach a series, it may not be so obvious why we should pick a given test over another. And that's common. And I would not feel too disheartened as I was learning this topic to struggle a little bit. Nevertheless, with a lot of practice, we can gain an intuition with regards to what type of test we should employ. Okay? So let's take a look at one example. We looked at the geometric series, and geometric series have the basic form that you see over here, where a is not equal to 0, otherwise it's the trivial series. And the geometric series will converge whenever the absolute value of r, the ratio, is strictly less than 1, and will diverge whenever the magnitude of r is greater than or equal to 1. And if the series does converge and we do have the absolute value of r strictly less than 1, then we also have this very useful formula. We actually have the summing from k equals 0, of course. Okay. So that was just a general form of series that we encountered, which has really simple properties. We also looked at the divergence test. And right off the bat, the divergence test is typically the first one you should be thinking about whenever approaching a series. Okay, it's really easy to sort of do, and it could save you a lot of headache with just going down the wrong road. Okay, if a series diverges, then no need to apply tests. We just check. We just use the divergence test, so it's pretty quick, and it works for pretty much any series. Okay, so this is just this general form. The idea of convergence there doesn't apply. In fact, the divergence test cannot show convergence. Okay, but it can show divergence. Okay, so you could be sure if a series diverges, but you can't be sure if it converges. And what is the condition for divergence? Well, we just check that the limit of the terms as k goes to infinity does not equal 0. So the limit of the series of the terms in the series do not go to 0. And again, the divergence test cannot be used to prove convergence. So what if you do get that the limit is 0? You cannot conclude that the series will converge. And the prime example is the harmonic series 1 over k, which diverges, but its terms do tend to 0. And another test was the integral test. Okay, and here we have some form of series that are amiable to the integral test. One, we need a function such that at the integers, at the positive integers, the function equals the terms of the series. And very importantly, f must be continuous, it must be positive, and it must be decreasing. So you got to check these if you plan to use the integral test. And if we do pass all of this, then we could take the integral of f, the improper integral, from the starting point to infinity. And if the integral converges, well, then the series converges. If the integral diverges, well, then the series diverges. Okay? So it's a very useful test. In fact, we could use the integral test to show that the harmonic series 1 over k diverges. Okay? But we must fulfill these. That's the sort of limitation there. And oftentimes it's not so easy to integrate some terms. For example, terms with a factorial. Okay, that's not easy to do an integral with terms with a factorial. And also, what's important is that the value of the integral, so the value of say it converges and you have the value of the improper integral there, is not the value of the series. Okay, so that's something to keep in mind. We also looked at the p-series test, and we basically used the integral test to demonstrate this. But if you have a series of this form, where you have 1 over k raised to the power of p, then when p is strictly greater than 1, you get convergence. When p is less than or equal to 1, you get divergence. Okay, and the p-series is very useful for comparison tests. Okay, that's so you might not always get that form, right? You'll get something similar or some other polynomial. Nevertheless, you could apply the limit comparison test or the direct comparison test using a series of this form. And it's easy to sort of memorize when you get convergence and when you get divergence for the p-series. We also looked at the ratio test. And this is a very useful, so it has a general form there. You take the absolute value, so it's also nice because, you know, if there are negatives or alternating terms, you could just, the absolute value takes them out. And you check the limit as k goes to infinity of a sub k plus 1 over a sub k. Okay? And if it's strictly less than 1, then you get convergence. If it's strictly greater than 1, you get divergence, and if it's equal to 1, it's inconclusive. And where does the ratio test shine the most? It shines a lot when you have exponents of k and factorials. Okay, you could see that with this sort of term, the factorials really get taken out. Okay, so it's super useful for those. We also looked at the root test. And again, here's just the general form of it. Works for all series. And we take the kth root of the absolute value of the ak term. And where does the root test shine? It mainly shines when you have a bunch of terms taken, you know, to the power of k. Okay, because the kth root just takes out that power of k right off the bat. So if you have you know, any number of terms and they're all exponentiated to k, well, it'd be useful to take a look at the root test there. And if this limit is strictly less than 1, you get convergence. If it's strictly greater than 1, you get divergence. And if it's equal to 1, then it's inconclusive. We also looked at the comparison test, the direct comparison test. And there we have a limitation that the terms must be positive. Okay. And, you know, just of note that if the first few finite terms are negative, that's okay. But eventually, you should have all terms being positive, because a finite number of terms never changes the convergence of a series. And so you'll get convergence whenever AK is less than BK and BK converges. Okay. You'll get divergence whenever AK is greater than BK and BK diverges. And of note here is that AK is the given series that you want to test, and you got to be clever and find what sort of BK is good to compare with. Okay, again, often this is one of these P series. We also have the limit comparison test, which is the more often used comparison test. And here, again, we have that AK must be strictly greater than 0, and BK is strictly greater than 0. So that's one of these limitations. And you check the limit of AK over BK, the provided. This is one that you provide or supply. And if you get convergence if it's equal to 0, or if it's greater than or equal to 0 but finite, so less than infinity means finite, and BK converges. Okay? if you have the limit 0 and bk diverges, you can't say anything about that. But here's the situation where you can positively say this series will converge. And if the limit as k goes to infinity of ak over bk is strictly greater than 0 and bk diverges, well then you can conclude that this series will diverge as well. Okay, so that's pretty useful there. And AK is given, and you must supply that BK. So again, typical one is the P series. We also looked at the alternating series test, and here we need this form here where you have a term that alternates and you have a strictly positive term. Okay, so you have one that strictly alternates between terms, the sign between terms. And here you just check that the limit as k goes to infinity of ak is equal to 0, and that the terms are decreasing, or they're non-increasing. Okay, so you need that the terms are non-increased, that ak plus 1 is less than or equal to ak. Okay, decreasing would imply non-increasing, but not the other way around. And of course these terms should be positive. And of note here is, when you do have an alternating series, this is a conclusive. This limit is conclusive. Okay, when you don't have an alternating series and you're just dealing with the divergence test and the limit equals 0, you can't say anything about it. But when the series is alternating and the limit is 0, then you can. Okay, it would converge. And you get divergence when the limit of the positive part of these terms is does not go to 0. Of note here is that you get a remainder term that's, the remainder is what you have after taking a partial sum. So if you sum the first n terms, then the remaining terms will be less than or equal to the next term that was left out. Okay, that's super useful for estimations. In the absolute convergence, this is more of a concept that if you have a series and the absolute value of the terms, the absolute value of the series, of the terms in the series converges, okay, then you get what's called absolute convergence. And absolute convergence implies convergence, so it's a stronger statement. All right, so let's look at some examples. Here we won't work out the details of the convergence, but merely take a conjecture about what would work and conclude with what sort of test should be used that's most convenient. So indicate which test should be used to test convergence for the following series, but do not work out the details. So we look at that. And again, off the bat, you should typically always apply the divergence test. No need to go through the trouble. And if you look at the divergence test, you see that top term has a 1 coefficient in front of the n, the bottom 2. So that limit is 1/2. And so it's not equal to 0, and the divergence test says that that series will diverge. You take a look at something like this. Okay, and here you got a polynomial. You will try the divergence test, but it's clear here that the numerator has a smaller power than the denominator, because don't forget that you are taking the square root there, and so the numerator has a power of n to the 3/2. Okay, whereas the denominator has the highest power of n cubed. And the limit comparison test is useful for these sort of rational functions. And a good way a good series to choose to compare with is basically one that you would get when you take the limit as n goes to infinity, right? As n is getting large, but before actually taking the asymptotic limit. So what you check what terms will dominate. Here the n cubed term will dominate once n grows large. It'll be much greater than n squared, so you neglect that, and that's why that 3n cubed is in the denominator. And over here, that 1 gets neglected as n gets very large, and so you take the dominating terms in the numerator and the denominator, and that's how you decide typically what series you'll compare with. We take a look at something like this, and this right here, you see, well, U substitution could be used, so the integral test is a good test to use there. You also see an exponentiation, so the ratio test would also work. And what about this? I mean, typically whenever you see this -1 to the k, not always, but typically, you'll want to use the alternating series test, take the limit as k goes to infinity. It's clear that this is 0, and so that's a quick check. Over here, we see a factorial, and factorial gives us a big hint. You see a factorial and exponential. And so that's a big hint that the ratio test should be used. Down here, you have, you see this 3 to the n, and typically you might want to do a geometric series test, okay? But that 2 is getting in the way, and it turns out that just a simple comparison test with this would work, okay? 1 over 3n, 3 raised to the power n, is greater than 1 over 2 plus 3n, right? This 2 makes the numerator greater, and hence this term would be less than 1 over 3n. So a direct comparison test there is well warranted. It's a quick proof. And you'll run into sometimes complicated looking ones. And what you could do here is break this series up into 2. So you'll have a k equals 1 to infinity. And we've looked at the properties of series that if both of these are convergent, then their sum should be convergent. Okay, and so we will break this up, and right off the bat we see that this is best tackled. You could break up this 3k plus 1 into a 3k times 3, and so you're looking at a geometric series there. And the other one, you're looking at an alternating series, okay? Now, that might not be so obvious, but notice that cosine of pi is negative, but cosine of 2 pi, cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1, and you get that alteration. So sort of a trick that one should be mindful of when, this is equal to 1 when k is even, and -1 when k is odd, and so you do actually get alternating there. Okay, and so it would be useful to do this using the alternating series test. And you could also write this as that. Okay, so that if k is an even number, or we don't want to do that, we'll write it as that. So when k is an even number, this will give you 1, and when k is an odd number, it'll give you -1. And so, okay, a bit of a trick there with the cosine, but nothing too challenging. We look at this, and we see this 1 over k raised to the power k, and this involves exponents, okay? So if you actually take this limit, you'll get an exponential term, which is not equal to 0, okay? And so there the divergence test is very useful. You have this indeterminate form, 1 to raised to the power infinity. So divergence test is always the first sort of quick look that you'll take. What about this? Okay. This looks like we have this k squared term, and you have this 1/4, okay, power. You're taking the fourth root, and so when that k squared term starts to dominate, you expect some sort of you'll have a 1 over k to the 1/2, and that p series test will give us that that is going to diverge. But here we could do a comparison. Sometimes you could also just sort of guess or write this in a nicer form. This is a perfect square. Notice here that you'll get k minus 3 squared there, okay, and so you'll get when you solve, this is going to be 2 over 4 to the 1/2, and you could even re-index this. So notice when we plug in 4, that first term there is going to be 1, so why not just start counting from 1 and change the variables so that j is equal to k minus 3, and so we'll get j to the 1/2, okay, and clearly that diverges by the p-series test, okay. So sometimes you could just rewrite the terms. What about this? You get this exponential, so it's worth trying the integral test. Looks like you'd have to do an integration by parts there, okay? Or, again, an exponential, the ratio test. And we look at this, and this is the limit comparison test. We see what dominates. If we wanted to choose that bk, how would we do it? We would say, well, bk, up there you'll get a 1/3 k squared. That's what's going to dominate, and you'll get a cube root 4, and so you'll have k 2/3 all over k 4/3. Okay, again, these are the terms that will dominate, and so that will give you the k to the minus 2/3. Okay, you always want to do a comparison using the strategy of seeing what will dominate in the numerator and the denominator, and you end up with a p-series test, and this bk will diverge. Okay, k to the that's p equals 2/3, which is less than or equal to 1, and so you will get divergence. So a bunch of strategies. Sometimes it's difficult to keep track of all of them. Nevertheless, we keep practicing. There are some general sort of ideas and rules that we could apply, some general forms that will hint to us what sort of test we should take. We should typically always start with a divergence test, and build. And as we practice more, we will build our intuition about what tests we should apply. And we also need a lot of persistence. Okay, so we don't give up.